Welcome back to che531. So we're going to pick up the discussion we had in the last lecture, which was on fourth order RK method. So we talked about the k values, and we basically said these k values are nothing but the slope of the curve at different x values. We talked about k1, k2, k3, and k4. So we proved that these k's are nothing but the slope of the function at different x values. Okay, so at the end of the day, RK4 is pretty much like RK2, but instead of having two k values, we're going to have 4. And we have to get the weighted average of the 4 k values to basically calculate the value of the function for the next delta x, or for the next x step. So in other words, we have the 4 k values here, which are evaluated at different x values. So the first one is at point xi, the second one is at point xi plus delta x over 2, third one is xi plus delta x over 2 as well, but then the y value is different. In k2 we have y1 or yi plus del x over 2 times k1. In k3 we have yi plus del x over 2 times k2, and in k4 we have del x times k3. Okay, so we already calculated the k's before. And at the end, the next y value is the current one plus, the weighted average of the k values, 1k1, 1k4, and then 2k2, 2k3. And divide by 6 because the sum of the coefficients is 6, 1 plus 2 plus 2 plus 1. Okay, so in the notes I also proved the order of accuracy of RK2 and RK4. We said RK2 is second order. That means again, if you increase or if you decrease your delta x by a factor of 10, then the arrow goes down by a factor of 100, which means 10 to the second power. So that is the second order. RK4 is actually fourth order. I don't think I have the proof here, but you can follow the same proof I have for RK2. Now, actually, I have two ways to prove that RK2 is second order using Taylor series, so I'll leave it for you guys to go ahead and take a look. I don't cover it in class. But basically, RK4 is of fourth order, which means if you lower delta x by a factor of 10, then the arrow goes down by a factor of 10 to the 4. So which means, a lot faster than RK2. Of course, if something is more accurate, we have to do more work. All right. So I think now it's the time to take a look at one example here. So the example that I have is actually right here. Let's solve the same equation we did using RK2 in Explicit Euler, and so let's look at the same problem we look at the other previous methods. This time now we use RK4. So the script is already on Blackboard. So this section of the script actually implements RK4. So I pretty much calculate the 4k values, and these 4k values are nothing but the function evaluation at 4 different x and y values. That's pretty much exactly what I had in the notes. So k1 is at point xi, yi. Well, my I starts from 2, so then I minus 1 is going to be 1. Alright, so we talked about this difference in the indices. Either I or I plus 1, I don't think that changes the result. Actually, it should not change the result. Okay, and then we have k2 at I plus del x over 2. k3 at I plus del x over 2, and then k4 at I plus del x. And on the y side, for k2 we have y plus del x times k1 over 2. k3 is y yi plus del x times k2 over 2. And then k4 is yi plus del x times k3. And here we average over the k values. We add it to the current y, we get the next y. And the rest is just plot the function in semi-log axis. So if I go ahead and run the code, you see that this time we get 3 curves. If I zoom in here, you see there are 3 curves. 2 of them are really close, and the red one is RK2, the black one is RK4, and you see that these are much closer than the... But maybe we can look at the Y3 value. So the dots are the explicit Euler, or forward Euler, and then the black and red, which are right here. These are coming from RK2 and RK4. So because they're more accurate and they're closer to the exact solution, and they stay together almost, and then they're a bit far from forward Euler, because forward Euler is first order. Okay, so that was RK4. So we saw the same example. Now another topic that I want to talk about is the step size. We can also make this RK4 a bit adaptive in terms of step size. So sometimes the function doesn't change much, and we don't want to have small step size, I mean small delta x. Sometimes function changes a lot, like if the slope of a function is really large and function changes drastically in a short distance along the x, then we want to have different step sizes. Like if the function doesn't increase or decrease much, then step size can be big. I mean, integration can take larger delta x. I mean, the error is not going to be much in that case because the function doesn't change much. If the function, in contrast, changes a lot, then we can take smaller delta step, or smaller delta x, or smaller step size, to keep, consistent accuracy throughout. So we don't want to calculate or predict a function more accurately in some region and less accurately in some other region. So I think in that case, we need to have adaptive step size, which means the step size can change as we go along the x-axis to solve the differential equation. So this is a very simple approach, and we can basically limit the step size by the percent of the y value. Let's say if the y is big, I'm going to take like p% of it to be the step size, or proportional to the p% of the y. If y is big, then p% of it is big. If y is small, then p% of it is small. So then I can change or adapt my delta x to go up and down proportional to the y value. Okay, so this is what it says. It says, well, this is the slope times delta x. So this is going to give us the delta y from prediction or from calculation, and this is going to be the p% of the current y. Okay, so we know that dy dx by definition is the right hand side of differential equation f. So we can set f times del x according to this equation to p times the y value, or p% of the y value, and then from here we can solve for delta x. So delta x is going to be p times y divided by 100 times f. Now, if we have multiple y values, like the example we saw before, we already had 3 y values, then we're going to have 3 ratios like this, from which we only pick the minimum. Okay, so that's going to be delta x. So here's an example. Let's say we want to solve this equation using we're using fourth order RK method, right? Using adaptive step size. So here's the script for it. So this is the function that we have here, And this is the boundary condition. At x equals 0, I have y equals 1. And let's say I pick only 1% of the y value to be the step size. Initially, the step size is this much. And we use RK4. So initially, we calculate or we update the delta x using the p% of the y value. And in fact, p% of the absolute value of it, because if f is negative, we don't want our delta x to be negative, right? So make sure you get the absolute value of it. Alright, then we go ahead and calculate the 4k values. And then we update the y. As soon as we update the y, we update the x value. We're just adding delta x to the current x value. Now we can update the delta x for the next cycle. And so that's going to be exactly the same equation. So it's going to be the p% of the absolute value of y divided by f. And that's the same equation we had here. So that's the p% of y divided by f. Okay, so let's run the code, and so I'm going to stop the code and run this one. So this is the function that is going down. It goes up at some region and it goes down again. So this is the function itself. This is the step size. So you see that when the function goes down with this constant slope, then the step size doesn't change, it's constant. Now here you see the function becomes flat, which means the function doesn't change much, so then the delta x can be large. So delta x goes up. Then here, the slope is really high, then delta x goes down, becomes smaller, because integration needs to be more accurate with the smaller step size. At this point, the slope changes a little bit, and the slope actually starts decreasing from here to here. And that's why you see the delta x goes up again. Here we have the smallest slope, which is almost 0. So our delta x is maximum. And then we again go down to a larger slope. And because of that, delta x goes down. Here the slope is fixed. That's why the delta x is fixed. So this is basically adaptive step size. We can change the step size as the function goes up and down based on the slope. So wherever the slope is fixed, right here and here, delta x is fixed. And when the slope is the minimum, then delta x is the maximum. And when the slope is the maximum, then delta x is minimum. Okay? So I hope this is clear how you can basically manipulate the algorithm that we learned in this class to be adaptive in the step size. Alright, so let's go back to our lecture note. So far we talked about explicit forward Euler, RK2, and RK4. Okay, so the next method we're going to talk about is explicit central differencing. This is explicit as it says, but it's more accurate than forward Euler. In reality, explicit methods is easier to deal with than implicit methods. Okay, so now we're going to look at another explicit method. And by the way, RK2 and RK4 are also explicit, but again, they're more involved. Like we have to calculate K1, K2, and the other ones K1, K2, K3, K4, and it might be a little bit difficult. So explicit forward Euler is the easiest, but it's less accurate. Now explicit central difference is a bit more difficult, but more accurate than explicit forward Euler. Okay, so in the next video I'll be talking about how to implement explicit central differencing and show you one example in MATLAB. So thank you so much for watching, and stay tuned for the next video.